x1 plus 2x2 plus 10x3 is equal to 61. So this is a dominant matrix. So fairly easy to see because these elements over here, they are the largest elements compared to the sum of the other two elements in the row. So we can proceed further. We'll also discuss later on when we come back to direct methods. What if the matrices are not dominant, and the concept of a pivotal element will come in a while. But we just assume that we have a single case where we can apply this method. So the first step, of course, was to write x1 as a function of x2 and x3, which in this case becomes 1 upon 10, 44 minus x2 minus 2x3. Then the second is to write x2 as a function of x1 and x3, which becomes 1 upon 10 as a function of x1 and x2, which is 1 upon 10, 61 minus x1 minus 2x2. So this is the first step. We write them in this form, and then we assume something. Initial assumption. To be on the safe side, we take all of them equal to 0 with no other better guesses available. So if you do this, then let's look at iteration 1. Okay, so let's look at iteration 1. When I substitute, so we first come to x1. So x1 is 1 upon 10, 44 minus x2 minus 2x3. So at x2 equals 0 and x3 equals 0, we find that x1 becomes equal to 44 by 10, which is nothing but 4.4. So now we have evaluated x1, which is this value. Now we come to x2. And x2 was 1 upon 10. So let me just say that we are calculating x1 in the first iteration using values in the 0th iteration, which is like this. So we are calculating x2 in the first iteration, which is 1 upon 10, which is 51 minus 2x1 minus x3, right? But now what happens is that now we have already obtained a value of x1 in this iteration. So calculating the value of x2 in the first iteration will be calculated using the value of x1 in the first iteration, but x3 of the 0th iteration. And someone is joined, just a second. So this is the difference, because if you remember when you were doing Jacobi, then the value of the x2 in the first iteration was also evaluated using the value of x1 in the 0th iteration, but that is the change. We don't use your x2 value. X2 in the first iteration will approximately come out to be equal to 4.22. You can check this. 4.22. So now you evaluated this value. Then we come to the value for x3 in the first iteration, and that will be given by 10, 61 minus x1 value in the first iteration, because we have this value here, minus 2 times x2 in the first iteration, because we have this value here. So if you do this, then you will get the value for x3 as 4.816. I I have this problem solved. That's why I'm writing on this. So at the end of first iteration, at the end of first iteration, your x1 is 4.4, your x2 is 4.22, and your x3 is 4.86. Now let's start with iteration 2. So in iteration 2, so x2 2 will be 1 over 10 44 minus x1. X1 on the second iteration is going to be 1 over 10 44 minus x2 in the first iteration minus 2 of x3 in the first iteration, because we don't have any other updated values for these two. So in second iteration it will be this. So if you do this, the value that one obtains is going to be 4. Then going further, x2 in the second iteration is going to be 1 over 10 51 minus 2 times x1 minus x3. But now we have an updated value for x1, which is 4.0154. So we will use that value here, and x3 will still remain at the value which is there in the first iteration, because that's the best value of x3 that we have. So if you do this, then your x2 in the second iteration, that becomes equal to 3.0148. And then x3 in the second iteration is 1 over 10 61 minus x1 in the second iteration minus 2x2 in the second iteration. So now you have these values as 4.0154 and 3.0148. So if you substitute these values, you will obtain something like 5.095. So after the second iteration, the values of x1, x2 and x3 are 4.0154. x2 is 2.0148 and x3 is 5.0955. So if you now run these iterations again and again, so I'm not going to do this, but I can tell you what the values are. So if you have iterations here, then x1, x2 and x3. This problem is rather long. So we have third iteration, fourth iteration, fifth iteration, sixth iteration, and up to seventh you start to converge. The values are as follows. You can check it and you can solve this problem when you're doing it on your own. You can check it. Zero, 3, 1, 6. 0.000. This would be 3.9746. 3.997. 1.0130. 1.01. So 1.01. Here type 0.01 should be 4.0. This is 124.971. 4.8001. 4.860. 4.994. So on the 8th iteration, you will get the answer. The correct answer is 3, 4, and 5 for this problem. So this is basically what Gauss Seidel method is, and since we are iterating with the values that we have found out in that iteration itself, this is going to converge faster than the Jacobi method. That is the basic thought that we generally have when we look into this. Right? So this is faster than Jacobi. Right? So I think this covers what we call it as the iterative methods. We are done with the iterative methods. We'll write the codes of the iterative methods in some time once we are done with all the methods. So now we look into what we call as direct methods. So this ends the iterative methods. So direct methods, I think we have done one, and then we move to iterative methods because they are less. And in Gauss elimination, so we will do Gauss elimination. There is something called as Gauss Jordan. There is something called as matrix inversion. And fourth is LU decomposition. Okay, so we had already done this. We need to do this and this. But before we do that, I'll just quickly revise Gauss elimination, and then we will move further how this needs to be done. So just a brief look into Gauss elimination. So in Gauss elimination, what we were doing was that using row operations, the coefficient matrix, or I should say probably the augmented matrix, was transformed to a triangular should probably write it like this. Just a second. So using row operations, the augmented matrix was transformed to another containing a triangular coefficient matrix. So basically, what a system like x3 equals b1, a21 x1, a22 x2, a23 x3 equals b2, a31 x1, a32 x2, a33 x3 equals b3. Suppose you had something like this, then the augmented matrix became a11, a12, it's not always necessary to write this dotted line, but clarity I'm just writing it. A21, A22, A23, and A31, A32, A33. So this is the augmented matrix to begin with, and once you perform row operations, you will get a matrix which will be basically A11 dash, A12 dash, A13 dash, B1 dash, 0, A22 dash, A23 dash, B2, 0 here, 0 here, and A33 dash. So this is what you will obtain. So once you have this, then you apply back substitution. And obtain the values of variables x1, x2, x3. So you can see from this equation that x3 is going to be basically p3 dash divided by p3 dash, and then from there, once you obtain x3, you can use the second equation to find out the value of x2, and then you can use the first equation to find out the value of x1, and you get all the values of x1, x2. This is And I think I asked a question in the exam also. So there is something that uh, I would want to mention now when we go towards looking at what are the shortcomings of this method and then to Gauss Jordan method. So there is a concept of pivot element. Pivot. So pivot element is actually in this method. The pivot element is actually the element with which you are basically dividing the other nodes. Like for example, if you look at this matrix here, uh, this matrix here, let me just uh, write this separately so that you can understand the process. So A11, A12, A13, A21, A22, A23, A31. Okay. Now, when we are applying row transformations, the first task for us is to ensure that a 0 comes here and a 0 comes here. And how are we doing that? We are applying transformations like R2 is equal to R2 minus A21 over A11 into R1. This is what we are doing. And we are applying transformations like R3 is equal to R3 minus A31 over A11 R1. This is what we are doing, right? To bring these two elements to 0. We don't care about what is happening here, but we want to bring these two elements to 0, so we apply this. So if you look at the denominator here of this ratio, and the denominator is A11 and A2. So in the first step, so this is probably step 1, right? In the first step, if this A11 is, say, a value which is 0, then we are stuck. We can't proceed further. And therefore, this A11 is called as the pivot. Pivot is like, if you look at the English word, pivot is considered to be the most central entity to any process. So you say if the pivot element is not proper, the process will just fail. So here also, A11 is the pivot element for step 1, in the sense that once this is, if this is weird, extremely small, or it is close to 0, what I mean by extremely small, or it is 0, then the process may just, not really work very well. So this is the pivot element in the first step. Okay. Now, once this entire process is over, you will be left with A11, A12, A13. This would be 0, this would be 0. Here then you will have A22 dash, A23 dash. Some change values will come. This first one will not really change much, because you're just doing elementary row transformations using these initials. So this will essentially remain the same. And then you will have something like A32 dash and say A23 dash, right? Now what is your task? Now your task is to fundamentally bring this element to 0. And how do you go about it? You go about it as R3 is equal to R3 minus A32 dash over A22 dash into R2, right? So now for this step, when you come to step 2, then if you look at the ratio, it is A22 dash which is central to the problem, that if this is 0, then the problem will again stop, or you'll be stuck, or you'll just fail in the method, because if this is 0, you can't do any transformation. So now what happens is that this element in this step becomes the pivot element. The pivot element, or which is called as pivot, right? And then once this is successfully performed, we will be left with A11, A12, A13. Double dash, for example, right? Now, then if you look at it, the third row, then automatically this is the pivot element. But over here, it doesn't really make any sense. Well, you can call it a pivot element, because if this is 0, then again you have an issue, because you cannot find x3. So in this step, you could say that this is the pivot. Okay. And then if you had a higher number of variables, if suppose you had a 4 cross 4, then of course you would have had another A34 double dash. So this would have made sense being pivot element. You can see that once you're performing these row operations, in every step the diagonal element becomes the pivot element, right? If you look at it, we start from here. So we started from here, this was the pivot element. Then after the row transformations, whatever came over here became the pivot element. Then after some row transformations, whatever came over here became the pivot element. And then this will continue. So pivot elements are essentially on the diagonal, but you cannot say that for this problem A11, A22 and A33 are pivot elements. No. A11 is a pivot element. Then after row transformations, whatever will be occupying this position at second row and second column, it will become the pivot element for step 2. Then whatever is going to occupy the position of the third row and third column will become the pivot element for the third step, and so on and so forth. And the Gauss elimination method requires that all the pivot elements be non-zero. Otherwise, you have a problem. You just get stuck with the problem. Okay? So, what are the issues with Gauss elimination? Let me just write down and we just look into it. So now we're looking at issues with Gauss elimination. So number one, if at any stage the pivot element at any stage the pivot element becomes zero, then the method fails. That is one issue. Okay. And then the second problem is, of course, we don't want a zero. We also don't want an extremely small number, because if you have an extremely small number, then in the ratio it becomes an extremely large number, and then God knows where you go with that number. Iterative process, and that generally happens if you're doing things with computer. These numbers tend to be so. Another issue is if at any stage the pivot element becomes very small compared to the other elements in the column. Then there is an issue again, because then what will happen is that so what will happen then is that division by a small number will result in basically multiplication by a large number. So this has its own problems. In numerical analysis, this has a very typical name. So if in the denominator you get a small number, it's called as a small denominator problem. That is what it is called. So we are not, because these methods are run in stepwise manner. Even if you write for direct methods, you have a step which keeps on repeating. and then you have some number of steps. Like for example, if you have a 3 cross 3 matrix, then you have 3 steps fundamentally to triangular matrix. You know, 3 steps. So in these methods, when you write a code using a computer, and the denominator with which you are dividing it, which basically means the pivot element, becomes small, then you essentially come to a multiplication which is very high, and then the subtraction by the element is going to result in some value which is uh, not very, will not sit pretty with the entire method, and you will not probably reach some kind of an answer which will be the answer expected. So those kind of problems can happen with Gauss elimination. There are definitely methods to avoid it to some extent, and that becomes the uh, basis of the next method, which is Gauss-Jordan method. I'll just quickly discuss it, but we'll do Gauss-Jordan method in tomorrow's class. So, one thing, of course, that can be done is that you can rearrange the rows so as to obtain a non-vanishing pivot. So suppose your pivot becomes 0. So what you can do is that you can see row transformations mean that you can interchange rows also, right? So like for example, if you look at this problem, and if suppose after doing all the steps in step 1, you would have reached a case where A22 is 0, then what you could have done is that you could have simply interchanged row A3 to the third row and second row. What I mean is this. So I'm just giving you an example. We'll look into this problem later. And then in tomorrow's class, suppose you have A11, A12, A13. You have 0 here, you have 0 here, and you have A22 bar, which also happens to be a 0, right? So, and you have A23, A23, and then you have A32 dash, and you have A33 dash. Now this pivot is 0. This is the pivot element that is 0. So Gauss elimination method will fail here. But if suppose I perform this thing, that R2 becomes equal to R3 and R3 becomes equal to R2, then this matrix can then be written as A1, A12, A13. This will be 0, A33 here, A3 here, A3. This will be 0. This is a non-zero element, and then you can proceed further. In fact, you don't need to proceed further because you've already obtained the triangular form. But this kind of a row transformation is possible. If you have a non-zero, if you have a 0 element at A11, then you can, even in the beginning of the problem, you can just interchange it with the second row, or you can interchange it with the third row. You can decide which row to interchange it with by looking at the problem, because then you'll be able to see whether it's just where it will be convenient to interchange it, which row you need to interchange it with. So that is something which is there. Then there are some methods like partial pivoting and complete pivoting, which we'll look into. So partial pivoting is that in the first elimination stage, the first column is searched for the largest element. That element is made pivot by the row exchange. So what basically it means is that suppose you're starting with this. We'll definitely look into it in the next class, but I'm just having a discussion here. So before the step 1 starts, you look at A11, you look at A21, you look at A31, and you see which element is the largest. Whatever element is the largest, you make it come in the first row by row transformation, and that becomes the pivot. In the second elimination stage, we will then search the second column for the largest element, leaving the first element of the second column. What I basically mean to say is, so you have chosen this chosen the largest element, made it the pivot, and done step 1. Now, once that is done and you come to step 2, then you look at the second column for the largest element. But now, because you have already done the first step, you will leave this element out. And you look the largest element in these two. Alright? So basically it's like this. You've done step 1, you leave all the elements of row 1. When you're done with step 2, you will leave all the elements of row 2. And when you're done with step 3, you leave all the elements of row 2. So now we are done with step 1. Now, if you look at the second column, you will only compare A22 dash and A32 dash, and you will see which one of them is the largest, and then you will do the row transformation and bring it in the pivot position, and then you will process the entire thing further. Then once that is done and you come to the third step, then you look at this. If suppose there was a 4x4 matrix, so in this case you don't really need to do anything, but if there was a 4x4 matrix, then you will look in the third column, but you will leave this element and you will leave this element, and you look at the third and fourth elements of this column, and then you will see which is the largest. So this is basically what is called as the partial pivot. Then complete pivoting is completely, it's a step further. You search the matrix for the largest element, and this element is brought up to the pivot position. And this could also, it may just require more than row transformations. You may also require change of variables. So x2 will become x1 or x1 will become x2, something like this you can do. Rearrange the equations also, not just to change the rows. You need to change, adjust the variables. So we'll look into that, and that will form the basis of Gauss Jordan elimination. So we look into these cases, partial pivoting, how partial pivoting will be applied, and then look into what is Gauss Jordan method of solving the problem, and but that all will happen in the next class. Right? So we'll start with partial pivoting. We'll look into some numericals of partial pivoting, and then we'll go into Gauss Jordan elimination in the first class. I will take classes this week entirely online, because my the kids in my house are highly suspected of COVID, so we all are isolated in some ways. I don't want to come and spread it around in JNU. So we'll have the classes this week in the online mode. Right? So even if I come to JNU, I'll keep my distance from the people and everybody else. But it's highly unlikely that I'll be there this week. So we'll have the classes online. And next week, I think I will kind of finish this unit of linear equations this week. So we'll start next week with coding, and I would want to do it in the class. So we'll get a laptops and things like that. Classes, write some algorithms of the blackboard, and you can run it on your systems and see how best we can do it. Right? Okay, then, thank you, and I'll see you.